Hello. So to continue on with our discussion of harmonics, we'd like to take a look at another way in which harmonics can occur. So just as a reminder, one of our key equations is that you can figure out the frequency of any wave by looking at the speed of that wave. In this case, it's v sub s for the speed of sound. And we can divide by the wavelength, and that will always give us the frequency of whatever, well, and in this case we'll be talking about, again, the modes of different harmonics. If you remember when we were talking about strings, one of the key concepts here was that for strings, that the speed of the wave as a transverse wave is not the same as the speed of sound. In fact, it could be slower, it could be faster, and that's a function of the tension and the mass per unit length. If you remember, we worked through a few examples where we saw that as we increased the tension, we saw that the speed got higher, and as we increased the mass per unit length, that the speed of the wave got slower. But now here we are talking about waves and pipes, and so the medium is no longer a string. The medium is sound itself again. So we're back to sound, pure sound. And the concept here is that the sound wave will be created and will be bouncing basically back and forth, and will create standing waves. And so we'll discuss that. There are a couple of video lectures that I want to highlight for you that will be available from Khan Academy below. And we're going to be using the speed of sound is 344 meters per second for all pipes. And of course, as you know, the temperature increases, it'll change a little bit. But for most of our example problems, we'll use this number here. So if we were to use a flute, we would see some sound wave that would be we would be entering in some air, and part of the air would go out and part of the air would go through the flute, and we're going to consider a flute to be like a pipe that is open at both ends, and because there's an opening here and there's an opening there, and we'll see in a moment what these two different types of pipes are. And the types of modes that we might experience are, let's take a look at this pressure one here on the right, is that the pressure is going to be the same pressure as it is in the atmosphere on both the left and the right. And so the possibilities that we have are that it becomes the highest pressure and lowest pressure fluctuating in the center. Or if we go to the second mode, we can see that it has exactly half the wavelength. That must mean it is twice the frequency, if you remember from our discussion before about harmonics. And again, you could also have three lobes. So these are places where it becomes high pressure, low pressure, high pressure, low pressure. And so those are the different kinds of modes. And one of the things that we'll also discuss here is that when you can go from a maximum pressure to a minimum pressure, this is also a place where the particle motion itself doesn't move very much. And so that's why we would say that the velocity or the displacement is the lowest. But at the moment, you can just focus on the right-hand graph at the moment. So remember that these are all sound waves, and this is the analysis that we're doing for a pipe that's open at both ends. So the result is going to be that we have, very similar to our discussion of harmonics before, is that we will have essentially your V over 2L and then multiplied by the mode number. So in other words, we're basically trying to figure out how we can fit a number of half wavelengths into this the length of this pipe. So there's one half wavelength, and just to break to the camera here, if I had a pipe here, and I have one half of a wavelength fitting in this space here. So here's my L. Then if I have this one half of a wavelength, here would be the other wavelength would be 2L. Then if lambda is equal to, or let's say half of a wavelength is equal to L, that means that lambda is equal to 2L. So if we go by our formula from before, that frequency is the speed divided by, or the speed or velocity divided by 2L, then we can see that the frequency is V over 2L. Now, if we fit in two half wavelengths, then we would have 2V over 2L. So that would be like if I fit in these two half wavelengths. So now, basically a wavelength is equal to L. And so if we plug back into our function that f is equal to v over lambda, we'll see that it's equal to v over L here. And again, if I'd go for 3 mode, the n equals to 3 mode here, you can see actually that if this is L, and this is 3 halves of wavelengths, or 1.5 wavelengths, we can see that 3 over 2L, lambda, is equal to L. This means that lambda is equal to 2L over 3. Now if we plug in for f equals to v over lambda, I can actually plug that in, and if you try that, you'll see that it's v over, and then it's 2L over 3, and I'll bring the 3 up here. So in other words, we have 3v over 2L. So that's why we have this expression that it's basically v over 2L times the mode number n. And then as we continue fitting in more and more half wavelengths, then we actually see that we can create higher frequencies. So there's another type of analysis which is for a pipe that is closed at one end. And so the way to think about this is that if it is closed, let's say on this left-hand side here, then the pressure is going to become biggest and smallest here, but at the end where we blow into, or sorry, at the end where it doesn't necessarily need to be where we blow into, but at the end where it's open, that the pressure will actually meet the pressure of the atmosphere. And so this means that you can fit a quarter wavelength, or 1, 2, 3 quarters of a wavelength, or 1, 2, 3, 4, 5 quarters of a wavelength into the pipe. And so when we try to do this, we actually can see that we can create a standing wave that has a certain number of quarter wavelengths fit in. So here's kind of an animation here that helps us to sort of think about what's going on here. If you look at the pressure graph at the bottom, you can actually see, just following up, for this red dot right here, it has maximum compression, maximum rarefaction, maximum compression, maximum rarefaction. And you can see that here in this red graph. If we move to the dot that's over a little bit to the side here, say motion is kind of exaggerated, but you can see that it's always has a cluster of neighbors that are about the same around it. And so that means that the pressure remains basically the same as atmospheric pressure, but its displacement is maximum. So that's a way to sort of think about that. Okay, and so the clarinet we're going to be considering as a cylindrical pipe to a good approximation. That's closed at one end, and it says closest here. It says closed at one end, and it's going to be open at the other end. So the formula that we'll have involved in here is going to be NV over 4L, because now we're going to be fitting quarter wavelengths into this. So we'll do some practice with these formulae, and I'll maybe also give a little bit more re-derivation toward the end of why it is that we have these two different formulae. So sometimes the best way to understand these formulae is to just apply them into practice. So let's take a look at this problem here. If we have a pipe that's open at both ends and it's 1.72 meters long, how can we figure out the frequency of the fundamental? So hopefully by this point, as you've been writing down notes from the lecture, you've written down our two key formulas. One of them is the frequency of modes for a pipe that is open at both ends, and the other one is for a pipe that is closed at one end and open at the other. Give you a moment to try and work this one out. Okay, so we're back. Hopefully you got that it was 100 hertz, but more importantly, how do we get there? This is a pipe that's open at both ends, and so the formula that we have associated here is that the frequency is equal to n times the speed over 2L. Now for the n equals to 1 mode, this is our fundamental, right? So we'll call this our fundamental. And so our frequency of number 1 is going to be 1 times v over 2L. So what we were given, the only thing that we were given is that L is 1.72 meters. So now we can start plugging in numbers. 344 meters per second is going to be our typical speed of a wave in air. Now granted, that number can change a bit, but we'll just assume room temperature for these examples. And then we'll divide by 2 times 1.72 meters. If you notice here, the meters cancels out, and we have 344 divided by 2 times 1.72, which is 3.44, and we'll have 1 over seconds, which is going to be hertz. Now if I did 344 divided by 3.44, that's the same thing as 100 divided by 1. So in other words, this is 100 hertz. Continuing on, what are the frequencies of a harmonics of a pipe that's open at both ends? What are the harmonics, right? So it's basically still the same problem as before, but what are the harmonics of the pipe that's open at both ends that's 1.72 meters long? Okay. All right, so hopefully you were able to sort of intuit this one, maybe even just glanced at your equation for the frequencies of modes that are of a pipe that's open at both ends, and you realize that 100, 200, 300 is the correct answer. Well, why is that? Going back to our equation here, if our original mode is 100 hertz, then F sub n is going to be n times F1. And if F1 is 100, then we'll have n equals to 100, n equals to 2, 200, n equals to 3, 3 times 100, or 300, etc. So you can see now that the subsequent modes, the higher order modes, are just going to be multiples of that fundamental. That's the thing that makes this a lot easier to calculate. All right, so again, we're working with a flute, which we'll be considering as a pipe that's open at both ends. What is the frequency of the third natural mode of a flute that has a length of 0.86 meters? Go ahead and try to work this one out. This is good practice for us here. Okay, so we're back. Hopefully, you've gotten that this one is 600 hertz. So let's take a look and try to figure out why that is actually the case. So again, I'm going to be working from this equation here. In fact, what I'll just do is make another piece of paper here like this. So here's our kind of equation that we're working from. Our length in this case is 0.86 meters. And our mode number in this case is not the fundamental mode, but it's n equals to 3 is what's asked for. So literally we can just plug into this formula here. So this formula will now become F3 is equal to 3 times 344 meters per second divided by 2 times 0.86. When you plug all those in together, you will get 600 hertz. Okay, so moving forward, so this is the picture here of the quarter waves fitting into this closed pipe. And one of the things that I want to, I want to emphasize to you is that in the open pipe, in the open at both ends pipe, you can have n equals to 1, 2, 3, 4, but in the pipe that's closed at one end, only the odd harmonics are present. So in other words, only n equals to 1 or n equals to 3 or 5 or 7, but not 2, 4, 6, or 8. So anyways, the way to read this formula here is it's NV over 4L, and the other big difference is that n can only be equal to 1, 3, 5, etc. So let's practice now. If I had a cylindrical pipe that was closed at one end, such as a clarinet, what might be the harmonics present for this clarinet in hertz? So you could look at this here when you're thinking, oh, well, we weren't really given a length here, so how do we figure this out? Well, let's go back to remembering what are the rules. For a pipe that's closed at one end, you can only have odd harmonics, which means that if you take 121 and you multiply 3 times that, it's definitely not going to be 233, so that one's out. 120, 3 times that is 360, so that's not it either, because this has an n equals to 2. This one right here looks quite possible, because 120, if you multiply that by 3, you're going to get 360. If you multiply that by 5, you're going to get 600. So in fact, the answer should be C. So in other words, going back to the pen and paper here, for the closed at one end pipe, F of n is equal to NV over 4L, and n can equal to 1, 3, 5, 7, etc. And so the point here is that if we started with 120, then 3 times 120 will be 360 hertz, and 5 times 120 will be 600 hertz. So that's how we get those different harmonics. So this will be F1, F3, F5. If we wanted F7, for example, F7 is going to be 7 times 120, which is, what is that? 7 times 120. 960, yeah, 960, no, yeah, 960 hertz. Anyway, so we basically, that's the way we calculate these things here. And actually, that's something that didn't sound right. But 600, what is 7 times 120? Let me just do it here. Get my calculator out. Seven times 120, 840. Okay, that's right. Okay. All right, so let's suppose that we got a flute that's 1 meter long, and you've closed all the tone holes. We'll talk about tone holes in a bit, but what frequencies are present? Well, this is just a cylinder 1 meter long, and it's a flute, if you remember, is a pipe that's open at both ends. That's because the air is able to equalize the pressure on both sides of this tube. So go ahead and try this out here. Okay, we're back, and hopefully you've gotten that it's 172, 344, and 516. Well, how do we get there? Well, for a pipe that's open at both ends, our formula is Fn is equal to Nv over 2L, and this time n can equal to 1, 2, 3, 4, etc. There's no, it doesn't have to be odd or anything like that. It's just any n can work. So if we have 1 meter, F1 is going to be 1 times 344 divided by 2 times 1 meter. And so 344 divided by 2 is going to be 172 hertz. So then, at that point, the only thing that we have to do then is we just recognize that the next one is going to be F2, which is going to be 2 times F1, which is going to be 2 times 172, which will be 344 hertz. And F3 is going to be 3 times F1, which is going to be 516 hertz. And so on. So we can always just continue to multiply those, and we'll get the different harmonics for a tube or a pipe that's open at both ends. So I also just want to mention some other types of shapes in case you're familiar with other instruments. So for example, like a conical pipe, for example, like maybe some kind of trumpet, the pressure waves look a little bit different. And so, for example, here there's no simple formula for F. So we looked at 2 idealized cases. And you can also see here that so here's our 2 sort of idealized archetypes here, the cylindrical tube open at both ends and a cylindrical pipe closed at one end, and I've given some examples of both of those types. And then a conical pipe might be an oboe or a saxophone, and there's also brass instruments such as a horn. And again, there's no exact, there is an exact formula, but it's not so simple of a formula as the ones that we looked for. So we looked for some idealized cases. So the mouthpieces for some brass instruments, they will act like a closed end. Especially imagine this trumpet piece here, is that we're applying our pressure on the mouthpiece, and so it's not open to the atmospheric pressure. And so this will actually be something that is closed at the end where your mouth is. A little bit more information just about brass instruments in case you're curious, just how does that kind of fit into the picture. And the way that notes are changed in some of these instruments is by either overblowing, which creates higher harmonics, and also changing the valves or changing the tone holes in the instrument. So the tone hole essentially is changing the length of the pipe effectively. So essentially, if you open up holes on the pipe, so let's see here, I should have a picture here of our flute. Our flute basically has a length of L, which could be the whole length of the flute, or from say here to here. But as I open up the tone holes from the bottom, maybe I have just this, this, and this open, then it makes it as if the pipe is shorter. And so as it's shorter, then we actually find that we get higher frequencies. So the shorter the effective length, the higher the frequency. So I think that's all that we have for now, and please check out the Khan Academy videos for some more instruction on how to make these calculations. And the two things that you should have getting clear now are the pipes that are open at both ends and pipes that are closed at one end and open at the other, and how to calculate those frequencies, both the fundamental and the harmonics. And one thing to really make sure you remember is that for a pipe that is closed at one end and open at the other, you're only expecting odd harmonics. So you will not get the 1, 2, 3, 4. You'll just get 1, 3, 5, etc. So hope that's helpful, and please see the Khan Academy videos for more practice.